You had questions. Can we discuss this?
My question was this BC transport. Yes, that's what I was saying.
That one?
Skew symmetric only,
No, 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 no.
in this matrix.
So you mean what BC transpose means?
It comes here, na? And
huh?
will it contribute for the main coupling effect, like coupling momentum? Coupling momentum, both the chain as well as this.
I mean, you look at this, because if you multiply this out, right? So all this, you have the MB, I mean, you have this matrix partitioning, and then of course you have this the corresponding C coherence matrix partitioning. And then if you multiply, and if you just do this explicitly, you multiply this out, then you get the two equations. And they are coupled, right? You see that you have the acceleration of the base, the acceleration of the joints, and the acceleration of the joints and the base. So they're fully coupled. And this is, and that's why they are all coupled. So what's the question?
That means this 2x2 matrix, na? In that I am saying that this is like skew symmetric. You are telling me that it is just
this
symmetric
one?
only.
This one?
Mm-hmm.
No, this is.
And first matrix.
So there's, again, it's important that maybe try to understand again the meaning of this thing. So we have this, what's it called? M. It's just called M. What is, so this is the kinetic energy of your system, right? It's always like this. The kinetic energy is always like the momentum. We said this is the momentum times the speed. And by knowing one property of the kinetic energy, you know exactly a property of M, which is what? Yeah, M is the mass matrix. It's a mass property. But mathematically, what properties does the matrix M have? Yes. So mathematically, okay, M has of course a dimension. It's called it's a square matrix. That's what I want to say. What else? What do you know about the kinetic energy? What can it be negative?
No.
No. Can it be zero?
No.
It can be zero. Can it be zero for non-zero S?
No, because nothing can have zero.
Exactly. No speed, no kinetic energy. And the conclusion is that this M must be positive definite. Because the kinetic energy is zero if and only if S is zero. Which means M is positive definite. You know this term? Yeah. Yeah, the eigenvalues are all positive. Okay, positive definite, that's an important point. And symmetric. And this you see immediately, of course, because the symmetry is already here, because when when you transpose this, you get exactly the same, because MBB and MCC are symmetric, and then if you do the transpose, then this becomes the transpose of this one. So what you suggested was that this was skew symmetric. No, it's not skew symmetric. It's even the opposite. It is positive definite. Because if it was skew symmetric, what if M would be skew symmetric? Yeah, but what would happen to this expression? I mean, generally, when you have a skew symmetric matrix,
transpose will be negative to the matrix.
Should be.
Yeah, that's right. That's right. I mean, let's have a different matrix because M is not skew symmetric. If M is skew symmetric, right, then A transpose is so. And what can you then say about, and let's say you have a vector X and X transpose. Again, this kind of quadratic form, because this is always what they call a quadratic form. What can you say about this? If A is skew symmetric? Just to follow up on you. A special case, you know, when we have this omega tilde, right? So we said this is a skew symmetric matrix that we construct from omega. Anyway, the skew symmetric matrix. And what do you know if you multiply this with X and X transpose from the left? Just as an example. Like a three example, three-dimensional example. What do you know? What is this?
One vector.
Yes, and what is it? It's the cross product of omega and X. Right? This is what you said. Now, if this is the cross product of X, I mean, okay, maybe, I shouldn't have used X actually. So X cross A. Oh, sorry. Omega cross X. This is how you did it before, right? And now you take the scalar product of this with X. What do you get? So you take any vector, cross product to X. And then you multiply what comes out with X.
And then scalar.
That's, huh? There are certainly a scalar, that's why there's a scalar product. Okay, you take a vector omega, some vector, for example omega, cross product X. What comes out is of course a vector which is orthogonal to X. Yeah, this is orthogonal to X. And now what's then about the scalar product? So you multiply a vector that is orthogonal to X with X.
0.
Correct, it's 0. So if, and that's just a special case, and you can show, I mean, just write it out, I mean, just make an example. And you will see that whenever A is, for example, skew symmetric, this is identically 0, always. And that's why this shouldn't be 0, it should be skew symmetric. Okay, this is where we left, I think this is where we stopped. No, where did we stop? I don't know. Somewhere. Yeah, that's where we stopped. So the question with the coupling, is it answered?
No, that MCC matrix.
The MCC matrix. Yeah, the MCC
contribute on coupling of both the.
So the MCC is actually the one that you know already, and this is what you probably see here, because the MCC is just the one that we had for the stationary kinematic chain. This is the generalized mass matrix for the stationary robot. So if the base wasn't there, this would just reduce to this one, right? So this is just the CC for chain change.
Just
Yeah. Exactly. And you see this, maybe you see it. Again, if you say special case, the base is not moving. So that's 0, this is 0, and the only thing is left is this term and this term, no, I'm sorry, this term, and this is exactly the motion equations of the kinematic chain when it's not moving.
Sir, how can you measure this all this parameter physically?
Which one?
This all of the measurement are calculated by mathematically. But how you can found this practically?
Yeah, that's a good point. I would like to show you some examples, maybe in the afternoon. Yeah. So the question was, how do we measure this physically? So the question is, what do you mean by measuring? Maybe just to repeat again, what goes into the equation? No, I'm lost actually. I'm not sure. Somewhere. So what goes into the equation? Maybe start from the kinematics. What do you have to do? You have to, first of all, find the screw coordinates of the joints. So this is what we said is easy to do, because you just need to measure some, the vectors of the joint axis, and that's it. And this goes in x, respectively y, as you, depends what you want to do. So that's the kinematics. That's kind of easily done, really easily done. So what's next? Dynamics. For the dynamics, you need, there's dynamics. You need the mass matrices. And this is what we did yesterday. So the mass matrices are, you need the mass of each body, and you need the moments of inertia, which is the inertia tensor, theta we call it, or sometimes we call J, or I. And that's it. That, of course, you have to find from, I don't know where. You have to compute this. I mean, you have your links of your system, and then you have to identify the mass parameters and the inertia moments. I mean, if you have a CAD system, then you get from a CAD system. Otherwise, that's always the thing. I mean, when you have a body and you have your links, you have to somehow measure them. And this what you meant? No. Yeah. So this is it. I mean, so that. By the way, there are methods for identification of dynamic parameters, right? What would be a good idea to identify, or what could you imagine how to identify, for example? I would like to know the mass and inertia of the links. So let's say you buy a robot, right? And you cannot disassemble it and weigh it, and so it's not possible. But I still want to identify those parameters. How could you possibly do this? So good point, what can you measure actually? Dimension, yeah. No, you have a control system. I mean, you have your robot, and you can do motion planning, right? You say go from there to there, and somehow it does it. So from your control system, what quantities can you access?
The angle of rotation.
The speed, the rotation angles, the speed of your joints. What else?
Torque. Can we measure torque? I think.
Yeah, and that's the thing. It's not always easy to get it, but you get the torque. What you most of the time really get is the current, the motor current, and that is somehow related, usually linearly by some motor constant or whatever, to the torque. So let's assume, and that is for most of the robots the case, that you can measure the torque. And when I say the torque, I mean the drive torque, right? So you actuate your rods, and then you get. Now, intuitively, it should be clear that the torque that you need to move the system has to do with the mass and so on. And now there is a whole business about this dynamic identification, in a sense that you generate trajectories, and such that are called persistent excitation trajectories. Because what you want to do, you want to see. In a sense, you want to feel in your motor current the effect of the inertia, right? I mean, simply saying that, I don't know. Look at the last one. So the last one, let's say you are kind of rotating about this axis, okay? And only the last one. What you probably are able to get somehow is the mass and inertia, and maybe even the center of mass of the last link. Because if you're turning here, and then your torque, that you need, is certainly related to the mass and the inertia of this last link. Okay. Now, if you do the same for this one here, for example, or this one, then of course it's a kind of a mixture, because then you have the effects of that inertia, and this inertia. But you can do this in a very nice way by using a linear regression, actually, to identify all this. There's lots of work on this, actually, but it's actually not too difficult to do. What you have to do is to find, as I was saying, you have to find, okay, when I was saying you rotate here and then here, yeah, but how do you do this? And this is why you have to find so-called persistent excitation trajectories. I mean, like motions, some are crazy motions of the robot that are exciting the dynamic parameters, so that you really get, for example, what you kind of a stupid way of actually trying to identify the mass of this system is by rotating about this axis, because you get nothing out of it, right? if I would like to identify the dynamics parameters of this last link, and I rotate about the vertical axis, you don't get much. I mean, you get something because you get the inertia about this axis, but it's almost invisible because the rest is too heavy. So you have to find certain trajectories, like motions, that are somehow so that, so to say, the motor currents, that means the torques, are influenced by the dynamic parameters of the system. Yeah, but that's not our topic. Okay, this was the dynamic parameters, which go somewhere here, right? So these are the dynamic parameters. And the rest, well, the rest is just computation. I mean, the rest is just, I mean, you know, forming these matrices, and the matrices again. Do we have it here on the slide? No, it's from yesterday. I'm not sure if I repeat it. I can maybe go here. Because this is what we did yesterday. There we go. Yeah. And then you form these matrices here, right? And that's more implementation but no measurement. And that's it actually. I'm not sure if I answered your question. I'm sure I didn't. Is this somehow what you wanted to know? No? So what was the question?
So how can you measure this parameter in physical, means experimentally?
Which one?
Coriolis parameter or centrifugal parameter, damping parameter, and others.
Okay, again,
coefficient.
So it's about the dynamic identification, about
how can you physically measure this, all this parameter?
Okay, so the question is, how do you measure, so to say, the mass of this system, of the links, possibly friction and damping of the joints? Yeah. That's a totally different topic. As I was saying, I mean, the dynamic parameters you get by using this persistent excitations. For the stiffness and damping of the joints, this is a different approach. What you do is like a frequency domain identification. So what you do is to okay, you have this robot picture in mind. So what you do, you have certain sweeps that you, I mean, like the motor torque. You give it a certain kind of excitation with a certain frequency. And then what you do, you measure the end effector, and then you have like a linear transmission channel. And from this you identify the what's the term? The term in English, the transfer function. Now I have it. The transfer function. And from this you identify you identify a model that comprises your, so essentially what you do, you say, we have a mass spring damper model for the joint and the links. And then, very simply speaking, and then you fit, so to say, the transfer function, or let's say the frequency response to this model. Not the other way around, the model to the frequency response. Of course, this depends on the pose, because when the robot is so differently, it changes the stiffness. Not the stiffness, but the transmission function, because it's a non-linear transmission function. And that's why you have to do this again in different poses. There's a lot of things that I could tell you, but maybe not now, because it's... So the message is there's lots of stuff there. I mean, I can send you some papers if you want to.
The spring mass system is a linear kind of system.
Yeah, that was not a good idea to say linear. So what you do, you have this robot, right? So a certain robotic chain, kinematic chain. So then you do each of the joints, you give it a certain frequency excitation with a certain frequency, and then you change the frequency, right? So you have like a sweep. But then you have to be very careful what kind of frequencies, what kind of excitations you use, because then you want to avoid nonlinear effects. Okay, different topic. Anyway, so, and then you measure at the end effector what comes out. And then what you get is input-output relation. And by assuming that the damping and the friction and the stiffnesses are linear, which is kind of a, this makes sense, you get a transfer function. So, and from this you get a frequency response, and from this frequency response, you identify a linear model that comprises your stiffnesses, your damping, and that's it. Because the masses, so the mass, the inertia parameter you have identified before. I mean, the chain is like, first of all, you have to calibrate your system. Calibrate means like kinematically geometrically calibrate. Just to know that you are exactly at the pose where you want to be. Second is you have to do the dynamic identification. So you do what I said, like this persistent excitation, you do high-speed motions, and then you measure the torques, and then you identify the mass and the inertia. And once you have all the inertias, then you can go and identify stiffness and damping. Because then you do, as I was saying, you measure the transfer function by assuming a linear model. Because at every state of the system, at every pose of the robot, the robot is fixed. The only thing that you're measuring is the transfer function due to the linear model that consists of the mass and the damping and the stiffness, which are linear. But you're right, the model is non-linear, which means that at every pose that might change. But the stiffness and the damping should not change. But the effect, what you measure is different, right? But it should be consistent. And yeah, this is how you do it. And there are many things to consider, because if you just use like random sine functions, for example, or like a chirp function, right? So you increase this frequency, you have to be very careful, because then you are exciting nonlinear effects, and this is not what you want. And that's why they use what's called odd random phase sine functions. So what you do, you have like a sine function with a certain frequency, and then the phase plus a phase offset, and the phase is random. Yeah, and so on. Yeah. We could talk about this. There are lots of papers on that.
Yes, sir. After course.
Yeah, it's absolutely right. This is a very important thing, because in the end, at the beginning even, you need, of course, the parameters. If you have no parameters, you can forget all the models. Yeah, and that's why it's model identification. Generally, what you do modeling, you do model identification, and then you do model-based control, right? Yeah. Okay. Did we finish this, or did we? I'm not sure.
That part you are doing.
Yeah. So that's okay, right? Yeah. Okay, good. Maybe we should not spend so much time on this. Yes. Okay. Good. Yeah. Maybe just to finish this one. I was saying there are two extremes. One is for example, the base is not moving, and just the robot is moving. If the base is not moving, then we have this equation, for example. I guess I have it also. This is the next slide. Yeah, exactly. Yeah, here. If the base is not moving, for example, then this is 0, right? This is 0, and this is 0, and so these are the two equations, and that's the first one for the base, and that was the one for the for the arm. If the base is not moving, this goes away, and we are left with this and that, with these coupling matrices. And what do you get then? You get the wrench at the base because of the motion of the robot. And that's exactly what I mentioned, because we talked about momentum, but this is about the wrench actually. This is about, so this gives you the wrench, I mean the torque and the force. And gravity, the gravity, yeah. And what you get then is the wrench, that means the force and the torque, at the foundation of your robot, right? And that's an important, interesting thing. I mean, normally when you have an industrial robot, you mount it strongly and nobody cares really, but you have to care about how much load you're actually introducing into the foundation and vibrations and so on. But for mobile robotics, it's even more interesting because you need to know that your system is not falling over, right? So if you do like high-speed motion and then the whole thing like tips over, then that's not a good idea. And that's why you have to do this model-based, because otherwise there's no way to do it. To identify the what you have to identify is somehow the load at the. If you have a mobile system like this with wheels, then you could look at the forces at the wheels, for example, right? But what you get out here, first of all, is the wrench. And then you have to do, with the wrench, you have to do something. Okay, let's say this is moving. I mean, this is a mobile platform, right? And there's a universal robot arm on top of it, and you move the robot arm. Then, and the base, let's say, is not moving. Then what you get from this equation is the torque and the force, expressed in the base frame somewhere, because of the motion, right? So, and then what you have to find, what you have to make sure is that the so-called, the zero moment point is within the support polygon of the mobile system. Okay, what do I mean by this? So let's say you have a mobile system with wheels. Okay, wheel. So if you have the mobile system with wheels, okay, so this is your top view or bottom view, I don't know, of this mobile platform. So now here you have one wheel, you have 4 wheels, right? This funny thing has actually 6, because there are driving wheels here. The other ones are just follower wheels. Okay, and how do I know that the system is not tipping over, it's not, falling? And this has to do with this so-called ZMP, the zero moment point. This comes originally from biomechanics. The question is, for example, when you are standing, right, or when you are walking, what's the condition for you not to fall over? Yes. Well, yeah, there's one kind of obvious argument could be the center of mass should be somehow in the support polygon of my feet, right? And when you say support polygon, like these are my feet, right? So it should be here somewhere in there, because otherwise I'm not able to, stabilize something here, which is not totally correct.
Net torque must be 0.
The net torque, exactly. The net torque must be 0. And there is exactly one point which is called the zero moment point, right? So there is for each of how to say the question. So there is one point. Okay. So I could determine the reaction force. When I'm standing here, I could determine the reaction force at a certain point. I mean, I have a frame somewhere on the ground, and then I can measure the torque and the force because of me standing here. There is a torque and a force. I mean, a moment and a force, which is called a torque. But there's one point where where this is reduced to a single force. Sometimes you have the feeling like it's in the middle, maybe not. So I bend a bit, and this is somewhere here. And exactly this, because if this point where your reaction torque is reduced to a pure force is, I don't know what I want to say. I don't know what to say. Yeah, anyway, so if this reaction torque is reduced to a pure force, no, nonsense. There's always a point where this reaction force reduces to a pure force. The question is this within the support polygon or outside? If it's inside, then it's stable. If it is outside, like sometimes here, then I can't stabilize myself, right? And the same is for the, and this is generally true. And you do the same, of course, for the mobile system. So the support polygon would be defined by the wheels, right? Because the wheels are the things that stabilize it. But you can also have like a table or stuff like this. And this is what we have here. There are formulas for computing it. This is very simple, but anyway, not shown here. And if you do, like this is what we did for this system. This was an Austrian research project. Yeah, I don't know what the motion was. It was a high-speed motion, and then you get whatever you get. So the good thing is the support. So this is the trajectory of the zero moment point, and apparently it's all the time within this within the support polygon. And this is of course including the full dynamics, right? What you said with the center of mass is more like a static consideration. Okay. Yep. Okay, good. Not sure. Yogesh is not here. Yeah, we could also look into the second equation. Just for completeness, to fill the time. What about the second one? That's the torque, actually, that you... so the second one is about... So I was saying, I mean, these are the motion equations, the coupled motion equations for the base, and this is for the joints, okay? What you could, for example, ask here again, it's like a special case of the joint not moving. Like, again, the system is locked. And this is maybe also interesting when you have like systems mounted somewhere. So you would like to stabilize your robot, right? But the robot itself is moving somewhere. Sometimes, I don't know, there are many applications, like on a vessel, for example. You have a robot on a vessel, right? The vessel is doing this, but the robot should be fixed. In space, it's also important. No, in space, it's... Anyway, there are applications for this. Okay, you get this out by looking into, again, the special case. And we always look at this cross coupling, right? So when I say the robot is not moving, the joints are locked, then this goes away and that goes away, and we are left with this one, right? So, and what it gives you are the joint torques, right? So the joint torques that you need to hold the system as it is when the base is doing a motion with the base twist VB, okay? Because when I say locked, I mean, what does it mean locked? I mean, normally you have to hold them, right? You have to control them still. And this is the torque that you need to hold it. Okay, and according to my clock, we're actually at the end, I guess, right?
We can come to do 12:15.
12:15, I think.
Oh, 12:15?
Yes.
Oh, I'm sorry, I'm sorry. Yeah, good, okay, then maybe let's finish this topic. I know it's a lot to take in, and that's the way it goes. Maybe let's go to a different topic. Or maybe let's go... Maybe have a different topic first, because the other one doesn't make the start in 15 minutes. How do you do the inverse kinematics of a robot? So the inverse kinematics, huh? Very good, exactly.
Geometrical solution.
Closed form solutions.
Yeah, exactly, so for some there are closed form solutions. For many there are no closed form solutions. For example, let's have this typical 60 freedom robot. So the inverse kinematics is, the thing is, it is not unique. right? So not unique means I give you an end effector pose. You see, it's all the same. But you get different inverse kinematic solution for this. So the joint angles are totally different. But they're all admissible, right? So which one do you like? Well, anyway, this is not a question. But yeah, it works. Looks good, yeah. Non-flip or flip? Where's flip? This one or that one? Yeah. Well, in the end, this is not a good idea just to look at one picture, because at one configuration, because your robot is doing a motion, and when you are starting, for example, here, it might be a good idea to start there, because in the end, the question is, are you reaching a limit? Because you have to do. The path normally is prescribed, right? So now you might actually come to a point where the inverse kinematic solution does not have a solution, because simply it's too too convoluted. So to say. Yeah. Anyway, but how do you solve it? How do you find these inverse kinematic solution? And there were two good answers. One said numerically and one said explicitly. Do you have an explicit closed form solution for this? There is actually one.
Yeah, but it takes a lot of time to even compute in math level. If degree of freedom or number of joint increases.
There was one of the kind of important results actually some time ago for the again for this risk partition robots. Okay, I mentioned this like this one again. We have 1, 2, 3 joints. They do the positioning, and then you have the what they call the wrist, like the human wrist, right? Because the last 3 joints they just do this orientation motion. And for this system, there is a closed form solution for the inverse kinematics. But I have to say it's more like a closed form solution algorithm, because you have to, there are some ifs and thens in there. But anyway, it's there. Okay, good. What do I say here? I don't know what I'm saying. Yeah, so let's say that we have, I'm sorry, I still have this C, which was H. Anyway, we have the homogeneous matrix that describes the end effector pose relative to the spatial frame, and I would like to have the joint coordinates according to this motion. Yes, and we have, as you already kind of suggested, we have different levels in the sense that we have the geometric inverse kinematic problem. So we really want to find the matrix C or H for a given matrix C, for a given end effector pose, you would like to have D or A joint coordinate vector Q. Okay, and that means like we would like to find the inverse of that function, right? Because we said that the forward kinematics is given by the product of the exponential. Now the inverse kinematics is, yeah, finding the inverse of the function. And that, of course, is not possible, generally not possible under P. Okay, and the other thing is the velocity inverse kinematics problem. So given the twist of the end effector, I would like to find the joint velocities. Yep. Okay, good. Yeah, which means that we have to find the inverse of that relation. And as we said, at the very first day, I guess, this is doable if J, for example, is square and full rank. What if J is not square?
Then pseudo inverse will happen.
Exactly, then you take the pseudo inverse. What is it? Kinematically, what kind of robot do we have if it's non-square? So we have a redundant robot, they call it, right? For example, if you have 7 joints, if that thing here has 7 joints, for example, we have 6, but let's say we have 7, then we have a redundant robot, because we have 6, so to say, output coordinates. The end effector has 6 coordinates, and we have 7 inputs. And they call it, this was in this area of human robot interaction. They started using them for whatever reason. And they call it anthropomorphic arm. Anthropomorphic arm, like human human, similar to humans. So what is the, how do we understand redundancy? What's the effect of redundancy?
achieve
In
complex
fact,
tasks.
solution, more than one solution.
More than one solution, that's a good point, yeah. And these are complex tasks, and yeah, so they are helpful for whatever complex means, complex tasks. They are more dexterous, right? In a sense that you can avoid obstacles, for example. So, I mean, they call it anthropomorphic arm because it kind of resembles the human arm. So the human arm, if you have a kind of simplified model, how many degrees of freedom does your arm have? I mean, forget about the fingers, of course. Now everybody counts. So how many do you have? So let's say we start here with the shoulder. Let's say we have a spherical joint, like a ball and soccer joint, which is not really true, but let's say. Well then we have, so this makes 3, right? So then we have one more, 4, then we have that one, 5, and then we still have the wrist. How many?
6.
Yeah, the thing is I already included this rotation. So we have 2 more left, which makes 7. So our arm has 1 degree of redundancy. And how do you feel this?
Quite comfortable.
You're quite comfortable with your arm, I know. No, the thing is that you have, as you said, I mean, the inverse kinematic solution is not unique. And you see this by saying, what does it mean? It means that for a given end effector pose, you have multiple inverse kinematic solution. And you can see this immediately. If you fix your arm, if you fix your hand, for example, you can still do motions, right? And this is the 1D motion, this 1 degree of freedom motion. Some are better, some are not so good, or not so good. So, and that's the important point. I mean, this is the important, reason for using them. They're more expensive in the sense that you have 1 more motor, 1 more joint, 1 more link, and so on. But sometimes seems to be okay. Okay. Good. Yeah. And as you said, the velocity inverse kinematics, maybe this one. The velocity inverse kinematics is kind of doable because you invert the matrix. Either you do an inverse either you do a kind of standard inverse, or you do a pseudo inverse, as you said. And by the way, in the pseudo inverse solution, you have a null space, which is the one that gives you the redundant motion. Okay. Yeah, what about now the geometric inverse kinematic problem? So let's say we are given the end effector pose, and given, for example, by our exponential mapping, f. Okay. Yeah. So this is actually our forward kinematic mapping. So we have the exponential mapping that gives you C of Q, right? For any joint angles, you plug them in and you get your end effector motion, pose. Then I have one desired end effector pose. Let's call it CD. Okay? So this is this homogeneous matrix and D for design. So the task is to find, and you start somewhere, right? So let's say you start from some Q, and if it is the 0 reference grid, whatever, you start somewhere. Then you say, okay, no, I need to find, so given this desired end effector pose, and what I need to find is the solution of this. I need to find a QD, like a joint coordinate vector, so that this is true, right? Because that's what I need to achieve. That this is equal to CD, okay? And by starting somewhere, I have to say, yeah, well, if I start somewhere, then there must be an offset so that I reach this point, okay? So my yet unknown joint vector, QD, is the one I'm starting plus some offset. Now the thing is how to find the offset. This is the big question. Yeah, and how do you define, now the thing is we have to find an error. So how do we find an error of the end effector pose? Yeah, that is, yeah. So we have given this CD, this is where we want to be. This is the homogeneous matrix that we should achieve. And then I have my forward, let's say here. Then I have my forward kinematic mapping, the exponential mapping. That gives you also something. So we have CD and we have C of Q. How do I find an error? So how much difference? I mean, how far am I away from the target? You said, subtract. You said subtract. So like saying that I take CD, right? So CD minus C of Q. This is what you said. Okay. What did we say about these homogeneous matrices? We talked about this Lie group stuff, right? And we said they form a group and so on. Under what operation did they form a group? Under multiplication. And also, does it really make sense to subtract homogeneous matrices? Yes, they have the same dimension, but not everything that has the same dimension should be subtracted. Okay, so you have like CD is like RD and little RD 1, 1. So this is my CD, right? And then you say I subtract the current rotation matrix and position vector, and then I have this. So what I'm getting is RD minus R, and here I get RD minus R, here I get 0, 0. I mean, first of all, what you get out of this is not the homogeneous transformation matrix anymore. Why? Because there's 0, not 1. And also, how do you, because what I would like to know is, when I say error, I would like to know the relative displacement actually of my current anti-vector pose relative to the desired pose, or the other way around, doesn't matter. And how do I get to the relative displacement of two frames? Exactly, it's a transformation. So it's this one. So you take the inverse times CD, and then you get a proper proper homogeneous transformation matrix that describes a proper frame transformation. Okay? So instead of using this, which is intuitively, I know, it's so obvious to say, but you should do this. Yeah, or the other way around. It doesn't make a difference. So, and this gives you the relative configuration of one frame relative to the other. And that's what we should use. Because then you have a proper homogeneous matrix, and we can use this matrix to solve the inverse kinematics. Okay, and we call this delta C, just for, yeah. Okay, yes. Okay, and there we go. Because once you have this delta C, you can actually proceed and say, okay, our so what I would like to have is that so this is delta C, right? So this is my current, so C of Q is my current configuration according to where I start, like some joint angles, and CD, this is given. And what I would like to achieve is that I can express this desired by a certain yet unknown QD, right? So I say, okay, there is a QD so that, you know, it gives me CD, but I don't know it. But anyway, this is correct. And then I do say, okay, this QD is, as we said, just the Q where I start from plus an offset, and the offset I need to compute. And now what you do now is, again, a Taylor expansion, right? So what you do now is like saying, okay, C inverse, of course, times, where am I now? Here. So you expand that, I mean, you expand this in a Taylor series, at the point Q, and you stop at the first. Yeah, and you truncate this at the after the first order, right? So just take the first partial derivative, because the Taylor expansion would go to infinity. And if you take a Taylor expansion of a matrix or any function that depends on a vector, it's the sum of the partials times delta Q. Yep, and there we are. So what's the difference here? Ah, yeah. So then we can maybe multiply this out. So this is C inverse and so on. Yeah, there we are. Because what is this? So C. Here should be CQ, of course. So CQ times inverse times CQ is the identity matrix. And what you're left with is this one. Now this was actually the definition of the Jacobian, of the forward kinematic Jacobian. What about time?
Yes, we can stop here.
Yeah, because maybe I'll go into detail after the lunch.